Sketching curves transformations. We've already seen that a curve with the following function, f of x plus a, will be transformed minus a units horizontally. And a curve with the function f of x plus a will be transformed vertically by a units. So here's f of x, is a parabola of some description. F of x plus 2 moves it minus 2 horizontally, or 2 units to the left. F of x plus 2 moves it 2 units vertically, or 2 units up. F of x plus 2, the x values reduce by 2 for the same y values. If you think about it, to get the same y value, you have to reduce the x value by 2. And f of x plus 2, the y values from the original function increase by 2. So that's how we're going to sketch the following functions. F of x squared, well, it's a standard curve, we know what it looks like. There it is, nicely sketched. We've got to label any known points. In this case we can see where it cuts the y-axis and also where it touches the x-axis at 0. Now if we're going to draw g of x, x plus 3 squared, we know it's been transformed by moving it minus 3 units, or 3 units to the left. So now it's over there. We always have to label any points where it cuts the axis. So minus 3 is where it touches the x-axis, and where it cuts the y-axis is when x is equal to 0. When x is 0, it's 0 plus 3 squared, 9, so it cuts the y-axis at 9. H of x, x squared plus 3, it moves it 3 units up. Again, label the places, 3, that's the only significant point there, that's h of x. Given that f of x is equal to x cubed, sketch the curve y equals f of x minus 1. State any locations where the graphs cut the axes. X cubed is a standard curve, we should be able to draw it. So that's f of x. F of x minus 1, we know it's going to be a translation of 1 to the right, a translation of positive 1. So now, instead of cutting at 0, it cuts at 1. We have to state where it cuts the axis though, so we also have to work out where it cuts the y-axis. Our original function was f of x, which is x cubed. F of x minus 1 is our new function, which is x minus 1 cubed. And when x is equal to 0, y is equal to minus 1. So that's where it cuts the y-axis at minus 1. Label all of the points when you sketch your graphs. Given that g of x is x minus 2, sketch the curve g of x plus 1. State any locations where the graphs crosses the axis. Well, let's draw g of x to start with. We know it's a quadratic, we know it's a u-shaped quadratic because there's a positive x squared, and we know it has solutions at 0 and 2. So we can sketch g of x. G of x plus 1, but we know what that's going to do as well. That's going to be a translation of minus 1 units, or 1 unit to the left. So instead of cutting before at 0 and 2, it's now going to cut at minus 1 and 1. And we also need to know where it cuts the y-axis. So g of x is x times x minus 2. G of x plus 1, if we replace x with x plus 1, then it's x plus 1 times x plus 1 minus 2, or x plus 1 times x minus 1. So when x is equal to 0, that means that if we've got 1 times minus 1, y is minus 1, so it cuts the y-axis at minus 1. given that h of x is 1 over x, sketch the curve y equals hx plus 1. State any locations where the graph crosses the axis and the equations of the asymptotes. Remember from a previous video, the asymptotes are the points the graph approaches but never gets to. 1 over x, we know what it looks like. It's a positive reciprocal, so it's in the first and the third quadrants. 1 over x plus 1 just means the whole thing is moved 1 up in the air. So now everything is moved 1 up. The asymptotes, well, x equals 0 or the y-axis is one of the asymptotes. The other asymptote has been shifted up. So the other asymptote is now, because the whole graph's been moved up, originally it was the x-axis, which is the line y is equal to 0. It's everything that's been moved up 1, so now it's the line y is equal to 1. We also need to work out where it crosses the x-axis. That's going to be where 1 over x plus 1 is equal to 0. We can solve that equation and we get that as that minus 1. We also need to be able to perform transformations of the form f(ax). This is a horizontal stretch of 1 over a. So f of 2x, it means you get the same y values using half of the x values. If it's a squiggle, it essentially means it will squiggle faster. And we also need to know that a, f of x, is a vertical stretch. So it stretches it vertically by a scale factor a. So a inside the function is a horizontal stretch. A times the function is a vertical stretch. So 2f of x is the same shape, but all the y values are twice as big for the same x values. So, given that fx is 9 minus x squared, sketch f of 2x. Firstly, we sketch the original graph. So we got, if x is 0, then 9 minus x squared, that means y is equal to 9. So that's where it crosses the y-axis. And then if y is equal to 0, then y equals 9 minus x squared, 3 plus x, 3 minus f if you factorize it. So it gives us that the places where it crosses the x-axis, or the solutions, are 3, 0 and minus 3, 0. That gives us all the information we need to plot the graph. We know the y-intercept, which is 9. We know the intercepts 3 and minus 3. Because it's minus x squared, we know it's an n-shaped quadratic. So we can sketch the original function looking like that. Minus 3, 3 and 9. F of 2 of x, if we substitute 2x in place of x, if x is equal to 0, then it's 9 minus 2x squared, so 9 minus 4x squared. So again, y is still equal to 9. So f of 2x doesn't change it vertically. However, if we now work out the solutions, 9 minus 4x squared, 3 plus 2x, 3 minus 2x when you factorize it, so minus 1.5 and 1.5, you can see it makes it narrower. So the effect of having f of 2x does to a graph, it makes it narrower. It's a horizontal stretch of 1 over a. 1 over 2, it's a half as big. It's the same height, it still goes through 9, it's just as half as big. To f of x, however, the original equation is doubled. So when x is 0, we get y equals 9 minus x squared. So now we've got 2 lots of 9 minus x squared. So 2 lots of 9 is 18. So now the y-intercept is at 18. But when we solve it, when y is 0, It's 2, 3 plus x, 3 minus x. So the solutions are in the same place, 3, 0 and minus 3, 0. So when you times the function outside to f of x, it doesn't make it any narrower or wider, it makes it taller or shorter. It's a vertical stretch of scale factor 2. So now it goes through minus 3, 3 still, but now it goes through 18. It's stretched vertically.